And please consider your questions when we have this august panel up in here in front of you. So who will be the first? I think, yeah, right?
So in a lot of the panel, or a lot of the discussion, there was kind of just detailed conversation about the processes, and we're talking about new processes. My question is generally, how far do you think we are from, or maybe we're there and it just didn't come up in conversation, from profitability in the process for a private company to say we can process the AMD to, do a market-driven reclamation process? Are we anywhere near that? Is there any idea of where we could get there in the near future? Or are we still like very firmly in government support research grant phase?
Okay, so I don't know that profit is going to be the primary motivation for the AMD treatment. So currently there's a cost to treat this water to get it to effluent limits or to the point where it won't cause problems in the aquatic environment. And there is a benefit. So, there's a cost-benefit ratio, comparative benefit. And I think we could argue that the treatment produces value. Now, we also have the potential to recover the rare earth elements and other elements if the supply chain is disrupted and we need these things. What are our options? There may be some additional costs. There's always going to be. So like when we think about fuels, now Marcellus gas is like the cheapest source of energy. So we talk about all kinds of alternative sources of energy. They're always going to have to compete with the cheapest supply or option. And that's true with the rare earth elements now and other elements. So they're still coming from outside the country at a lower cost than we can recover them from these unconventional sources. But the question then is, will they be available in the future? And so this is why we're right now researching the opportunities to develop these technologies and alternative sources. And I don't believe in general there is a profit motive for that work. There is some demonstration in West Virginia where they're using full-scale treatment facilities to recover rare earth elements, and they're saying they're getting these great high-purity products. But what you don't know is how much it costs them. And they're getting a lot of government money to build these treatment plants and so on and so forth. It's not explicit, it's not transparent. So that's my 2 bits. I think we can offset some of the expense for water treatment, but I don't think we're going to make money from the whole process.
Yeah, and I echo that one, that right now there are a lot of money paid by the taxpayer for the treatment of those acid mine drainage, and then the product can offset some of the treatment costs. So, like, again, echoing that one.
So I would like to add something to that. In hard rock mining and coal mining, we find REEs, but there are not any per se, other than lithium, REE mines that you can go and just mine those materials. They're often associated with different ore bodies, both in hard rock and in coal. One key to production of REEs from coal is that they need a carbon co-products for the economics to work. That was another takeaway from this presentation by University of Texas. And anthracite coal right now, it's a metallurgical coal. It's been named in an emergency executive order as an emergency fuel source. I would note in Virginia, they're mining anthracite coal, Calgon is, to use as carbon infiltration, filtration products. So there's a lot of uses for the carbon. And the one advantage this area has is there's a lot of available carbon laying on the surface in that coal. So I think that's something to consider in terms of you know, it may not have the highest RE values, but it does have a lot of the other components that would be needed to make it feasible in terms of large-scale production.
Yeah, I just want to add to what Chuck said about the profit motive. One of the reasons we find ourselves in the situation we are now is that the markets have been manipulated globally to undercut that profit motive, so that if it becomes profitable to perform one of these extractions, we see the price drop. I mean, this is what's hurt mining in this country for a period of time now. So I think there is a reason to fund the research, the development. And then also I wanted to mention that when I've attended workshops on the mine of the future, one of the themes that's common to them is that there'll be much less waste in the future. And if you look at the petroleum industry and what is left over as waste from the extraction of oil, there's almost none now. And what there is back in the ground for the most part. So, you know, they've turned all of their waste products into usable things. We're wearing them. Virtually all the plastics, the synthetics, so forth, are former waste. I think mining has potential to do similarly, of course. And we're seeing a lot more interest in solution mining, in situ mining, where nothing leaves the ground really, and that's where your reactions are occurring, where the extractions effectively are occurring.
Yeah, I just want to clarify, I'm a policy guy, so I'm just thinking, like, how do we get the motivations behind further investment and support of these processes without, you know, lawmakers saying, like, well, what's the end game here besides just dumping government funds into this process that is very expensive? So I'm just trying to think of how can we hook.
If I may, on the policy side, one of the things that in Pennsylvania we need is have the right of the mineral. So it has been cleared out in the state of the West Virginia, and they just passed a law. So whoever treating it has the right of the minerals as well. But right now, let's say if someone comes and recover critical minerals from the acid mine drainage in this region, so who has the right of that one? The one that has the coal mine that is charged from the coal mine, or the one that who is like collecting those one, or the person that, or the company that is treating those ones. So when it's come there, like some dollar come to the situation and then to the picture, so then there are gonna be a lot of conflict. So resolving those one in the state of the Pennsylvania would be very helpful. West Virginia already sorted out recently, so in the state of Pennsylvania, we need to sort that one out as well on thermal policy.
So, yes, on that matter, that's important to have our expectations tempered with realism. Of course, when you speak about a cost offset, to the extent that remediation can be self-funding, to some extent, that's of course welcome, but I think we understand. Over here.
Yeah, I'm sitting wondering about the scope of a plant that would be necessary to do all of this type of work. I mean, you're talking about a petrochemical processing type plant. You know, each one of these AMD treatments plants in the anthracite are going to be 10, 12 acres just for taking the iron or aluminum out of them. When we start putting on a process to take out 17 other items and 24 other items, and sounds to me like it would look like South Philadelphia, each one of them. And you know, I can't imagine that the people that have complained about having all of the waste around are going to be that happy about having all of the plants around.
Okay, so a lot of what we were talking about, Dr. Reze and I, with respect to water treatment, would be stepwise in maybe a conventional treatment facility, not necessarily greatly expansion of the size of the facility, but more precise targeting of pH values, et cetera, where we can accomplish a certain separation of, say, iron first, and then maybe aluminum, ultimately concentrating the other constituents that would not have been removed at those lower pH values. So it's a more precise approach to treatment that's being used now. We're just not dumping in, we're not going to pH 9. We're not just trying to get rid of everything at once. Maybe, like fracking, which, yeah, there's, well, right, so that would be like different temperature-dependent endpoints where you can, it may not require much enlargement. There may be, well, certainly there's going to be extra steps. But the biggest part of like a conventional plant might be the clarifiers or the ponds or something. And there may be steps before you get to that point or between where other things are achieved. I can't tell you. It could very well be, but you're also, it could be big, it may not be. Like these passive systems, a lot of the recovery actually occurs in the limestone beds, like in the manganese beds, et cetera. They're not any bigger, they're not built for that purpose. It just so happens that there's a concentration of rare earth elements accumulating in that step, which is being done anyway. So it's not necessarily an approach that was by design intended to concentrate the rare earths. It was by accident. We know this now, and we're starting to use more, innovative approaches to achieve the same thing in a little more controlled fashion. Well, and then another thing just to think about, I showed a couple slides. I said in the bituminous region, we have a lot of the higher concentrations at multiple sites, especially some coal refuse disposal facilities. In the anthracite region, the concentrations tend to be lower, but the loads are high because of the flows. Those are going to be the hard ones to really. Well, the quantity, but it may cost a lot more to achieve those recoveries when you're having to treat that much more water. It's just like you're saying, you got this big facility, right? Those cost more than a smaller plant to operate, so.
And I would add that realistically, because the mine pool under Shamokin extends through a drainage divide and extends quite a bit down the middle anthracite field, I would envision that you'd have to have several treatment facilities to draw down the mine pool. They'd be a clarifier unit like West Virginia is using in Muddy Creek watershed. It's in a very rural area just along the road, and they have a couple of clarifiers. It may be, I'm only speaking to water treatment, not refuse, but yeah, I would envision that they would have to find several locations, and I think Tetra Tech's already working on that to identify the best areas to situate a treatment facility.
Yep. My question goes more with the solid material, like if it's refuse or coal ash. And I know they've tested coal ash and stuff, but with whatever processes that would be need to extract the rare earths, will they change the character or the designation, if you will, of the other material? Like the coal refuse would be great if you could extract the rare earths and then process the refuse as a carbon source like you normally would. But if it changed it to industrial waste, you're going to end up with all that material with only a little extracted out of it, and now you can't utilize the material. And the same with coal ash. Coal ash has been beneficial use, but if you extract it out of coal ash and now that becomes a hazardous waste, you're confronted with a big problem.
Wait till we, okay.
Yep, it all plays together.
All right, but please, go ahead. Dan's question.
On the coal refuse, if I may, on the coal refuse material, so there were a lot of studies done and pilot scale testing was done for the extraction of the rare earth elements from the coal refuse piles from the different coal seams at the University of Kentucky. So then the conclusion was that the amount of the physical separation process is required with the current technologies, and also the downstream processes was not economic. So that was a conclusion of that study. And then, so the reason for that one was the rare earth elements that are very finely disseminated within the coal refuse material. So if you want to extract them, it would require a lot of like fine comminution and then separation through the physical separation, and then do the leaching processes and then extraction. So one of the best approaches to address the challenge that you mentioned, to not changing the characterization of that one, and then while still extracting those one, it would be potentially the heap leaching process that the Kurowater presented, that reusing some of the acid mine drainage to re-extracting, send it on top of those material, sparkling it on top of those one, and re-extracting more out of those refuse pile. So this way you're removing the steps for the physical separation and concentration of the rare earth elements, and then you can bring it directly to the acid mine drainage or leachate that you have it. So then over there also, one of the challenges would be then you gotta work on the technology to make sure that you have the best efficient way to remove the iron load that you have it in your system, because otherwise if you don't take care of it through the iron removal, so then the cost for the downstream purification process is going to be high. But in terms of the process, so then heap leaching that the Kurowater presented is the most appropriate approach to not cause any issue for the changing physical property. At the same time, extract, is it gonna recover 100% of that one? No, but it increases the recovery of that one at the minimal cost, and that can be subjected to the downstream purification and treatment process.
Yeah, so I would add that the source of acidity in the coal refuse, pyrite, is a finite quantity of material, and as you leach it over time, you essentially detoxify that waste. So the end product may not be more of a concern, but perhaps less of a concern. And in fact, the same sort of process occurs in the environment. You know, these sites that are, abandoned 50 years ago, the discharges from the old mines, over time, they get less toxic. They're less acidic, there's less metals, et cetera. And that's actually a relevant, I'm kind of sidestepping. When we talk about the work I did in 1999, is that a basis to plan forward now? No, we need to collect data now on what are the characteristics of these mine discharges 30 years later, whatever, how much time that's been. We need to, because they change over time. On a decadal scale, these discharges become less mineralized. And so that's an issue I think needs to be considered when we're talking about this potential resource. If you go to a discharge that's just recently developed, you remember the Shadle discharge? We get these, in the anthracite region, this was a pH 3 discharge. It had some of the highest concentrations. We were all excited by it, did a bunch of work there. 8-10 years later, it's near neutral. It sort of, after it floods, things change. And so you need to plan that, just like a mine, the dual twin, what did you call it? The digital twin. You need to anticipate how this source material may vary spatially and temporally. And that is a real critical aspect to the economics. Let me talk about your digital.
This may follow on, but I forget your name, sir, I'm sorry. Fred. Is the system that you're building, is it, and I'm mostly a layperson here, is it like Google Earth of rare earth that we sort of do it all and have one map? Or if you start to mine these sites, as you sort of peel off layers of the mineral lasagna, do you need to redo it? Or is there a possible need to redo it because of how much depth you can get? I hope that makes sense.
Yeah, Is this on? Is this on? That's a great question. So we envision at least a single survey to do a characterization, but as you peel away earth, as you excavate it, or if you're manipulating the system in solution mining, injecting a lixiviant, moving this material, this fluid around in the subsurface to mobilize a mineral of interest and dissolve it, and mobilize it, and then extract it, as is done in uranium and certain other minerals. We could look at that. We could look at that over time. So doing time-lapse geophysics becomes much more like functional MRI. So if you've had medical imaging done before, you can either go and get a single scan and might find a broken bone or whatnot. But if they're interested in the dynamics of the system, how your heart is operating or your lungs or whatnot, blood is moving around, you'll get a time-lapse video of that process. And we can do the same for the subsurface. So we can watch fluids moving, we can watch water infiltrating. If there are contrasts in the total dissolved solids and the electrical conductivity of the fluids, that's a great tracer that we can use as it moves through the system. So I see a lot of advantage to doing this in time-lapse mode, and that's again where the drones are motivated in part, because they're very easy to mission, to go out and do the same thing over and over and over again without a whole lot of labor. Yeah, I see great value in repeat, especially at active mines. And as you do peel away the earth and you have data on what you've recovered, what the mineral content is, or what the properties of it are, that helps with the interpretation of what's in the next layer you're about to peel away.
So we probably want to stick with the schedule and have a break at 10:30 to be fair to our other presenters and fair to us all. So maybe just one question. Who would, I saw your hand first. Sorry.
It was mentioned that a lot of the REs are concentrated in the underclays and shale partings. Has there been any efforts to pinpoint where they would be located, both stratigraphically and across the coal field laterally? I was actually thinking one way to do it is when some of the coal companies are doing exploration drilling, if you just had an XRF scan the partings as you're coming up, if you know where to look for it, it could help in the future. You could even separate these layers if you could find them, and they could be removed and separated with the coal.
Okay, so there has been some work done. Most of the chemical characterization has been on the coal itself. And so there's a huge database on coal quality that includes rare earth elements and other elements of interest, but there is relatively little data on the other units, the associated, shales and underclays. There has been some focus on that more recently, not in the anthracite region that I'm aware of. And then just the idea that these refuse materials, the carbon value, they float that material, to separate the carbon. They basically use a process that separates the high carbon material from the non-carbon. Well, that non-carbon material is the underclay. It is the shale partings. It's the non-coal that after the carbon part is separated, now you've got a concentrate that maybe could be considered as an option for further recovery.
I would just note as a follow-up study to my ROAR proposal, we had thought about looking at a couple of coal breakers in the area and doing ground penetrating radar surveys, because then you could differentiate the parting materials from the coal, and maybe we could pinpoint, specifically what materials do contain higher quantities of REE. So that would be a good area for future study.
And on the bituminous region, there have been some studies like lower Catanine coal has also elevated content, the underclay of the lower Catanine coal. So because when the rain and a lot of filtrate material go through the coal, so on the underclay for the coal, like is not porous, so it start capturing all of those one, and ion exchange happens. So then a lot of like elements also are concentrated in the underclays. So then lower Katanning has shown some potential for the elevated content of the rare earth elements and the lithium and some of the other ones.
Okay, Mohammed, you have the last word. Let's break here. We'll be